Hello everyone, welcome to this lesson. So in this lesson we're going to go through the Python code for the false position method. Now if you remember, the false position method is actually an improvement over the bisection method because now we take into account the function value at the upper and lower limit. And we have explained in the concept lesson that the way we have derived the false position is we have connected a line between the function value at the upper limit, function value at the lower limit, and where the that line intercepts the x-axis is our estimation of the root. And we have derived this equation by the concept of similar triangles, that the slope of these two is the same, and we have put the two slopes equal to each other, and we have created the false position method. We have gone through the first application of it, and it gave us, with an upper limit of course of 2.5, lower limit of 1, and it gave us an XR of 1.8 and a true error of 10%. We gone through the second application. It gave us 1.9697 with 1.515% error compared to the true root at 2. And then we went to the third application at 1.9956 with a 0.218% error. So you can see it's actually a very, very effective technique. In just 3 applications, we now have a approximation with only 0.218% error. Now in this lesson we're going to be creating the Python code for the false position, and it's going to be a very, very simple code to develop because it's almost identical to the bisection method with only one line of code difference. So let's actually see. So here, as you can see, everything is almost the same. That here we have the function value that we're dealing with, x squared minus x minus 2. Here we have the initial guesses. In this case, we're going to start with lower limit of 1, upper limit of 2.5. Same initializations. Here's the main loop. We define what the XR is. Then we go identify the section where the root exists. Then we calculate the approximate and true error, store the approximation, count the next application of whatever method we're doing, then we repeat. Now I want you to look a little bit closer at this loop. Is that now what XR is equal to is different. When I go back to the bisection, which is XR is the upper limit plus the lower limit divided by 2, now the XR is going to be defined in this equation. So the only difference in this code from the bisection code is now I am equating XR using this equation here, which is identical to what we have up here. So let's actually now, given that this is how XR is defined, let's actually see how the false position is going to compare to the bisection. So I'm going to start with an upper limit of 2.5, lower limit of 1, and let's start with an error of 0.01 and see how many applications of the false position is it going to take to go below 0.1%. So as you can see, it takes 5 applications of the false position. We got to an error of 0.027, and you can see the root here is 1.999911. So very, very accurate approximation. So let's actually adjust the true error here to 2 so we can get accurate values for the true error as well. So if I run this, now we have also accurate values for the true error. So let's actually go back to the bisection because I want you to see the differences in both. So let's actually do an error of 0.01, see how many iterations. So if you remember, it took 10 different iterations and we got to an error of 0.073 at 2.0000488. So 10 applications and 0.073. If you look at here, we have 5 applications and we're actually lower than that, 0.027. So you can actually see the effectiveness of the false position, half of the number of applications, and we even got an even better error estimation here. So let's actually go to how many applications it's going to take to go to 0.01. So 6 different applications, 0.0038. So if I go to the bisection and do 0.01 as well, 13 different applications as opposed to 6 applications with this one. Let's actually go a little bit further to 0.01. So 7 different applications to go below 0.001%. And you can see almost 2 here. And this one, if you remember, it should give us, if I remember correctly, 17 different 17 different iterations for us to go below 0.001%. So you can see the effectiveness of actually factoring in the values of the function values of the upper lower limit in finding the root. So if you remember, this equation has actually two roots. So actually, let's find the root at -1. So I'm going to do a lower limit of -1.5 and an upper limit of 0. Let's actually examine it at 0.01, and let's change the true error here to -1, and this one as well to -1. So still 5 different iterations to find the -1 root at an approximation below 0.1%. Let's actually compare it to the bisection. Let's say -1.5 and 0, and start with an error of 0.1%. So this takes 11 different iterations. This takes 5. If I do 0.01, this takes 14 different iterations, and this one takes 6 different iterations, and this one probably will take 7 to get below 0.001. So actually it took 8, and you can see it's almost exactly -1. And if I go to 0.01 up here, 18 different iterations to get below 0.01, and you can see here -1 for the root. In this lesson, to kind of recap, we have introduced briefly again what is the false position method. We have introduced the code, and the only difference in the code is now you're going to be defining XR using this equation that we have introduced here. We have also introduced how the false position is actually superior to the bisection by factoring in the function values at the upper and lower limit, and we have found that we can actually get to this even more accurate approximations of the root in almost half the iterations. So in the next lesson, we're going to be going to the next type of root finding techniques, which are open methods, and we're going to be starting with the Newton-Raphson. And of course, we're going to be comparing the Newton-Raphson as we're developing the Python code to the bracketing methods to see whether or not open methods are superior or bracketing methods are. Well, that's it for this lesson, and I will see you in the next lesson.